Yeah. Okay. So do you want to get into this?
Yeah. Quick? This was tough.
This was so, I have to say, this was unenjoyable. This particular model was like, I felt like I was back in college. And it was
me too, like cramming for the final, like, oh my God.
Yes. So this was like the Resonance Science module 3, which was modern physics. And they basically went from the history of everything in physics up till, you know, the Higgs boson and like what they're doing now with like quantum waves. And I mean, I'm just kind of going like
string theory. They went through everything.
String theory. They went through everything. And I'm kind of going like, I had to relearn. The only thing I didn't have to do is assignments with equations. They gave us the equations.
That's
and we
true.
had to look at the equations, but I didn't actually have to do my own mathematics on it. Other than that, like you went through, in fact, I went through more history lesson of physics right now than I even did when I was in college. And like I took 4 semesters of physics in like a university level. So like I was just going like, geez, this was so overwhelming.
And wow. All right, good. I don't feel so bad because I had none of that. Like I said, my last course in science was geology in college. And that was like the last one I took. I didn't even take physics in high school. I took chemistry. Wow. Yeah. Chemistry was the last
like torture for you then.
It was, I mean, I actually like this kind of stuff, but getting into the nitty gritty, I like the esoteric part of it.
I know.
that's what calls me to it, really. The physics, the whole universe, like the whole questioning about it, but all the math involved is pretty intense.
Yeah. I mean, like for me, I also like I like some of this stuff too, but I don't know how much detail I need to go into each individual little aspect of it, you know, because the other thing is like, you can tell me what, you know, what the laws of motion are or whatever, but I'm not going to memorize them for all. And even if I memorize them, I'll memorize them for the test, but they're not going to be like, you know, something that is just going to stick in my memory for all time. Like, I mean,
it's not for practical purposes in a sense.
No. And if I need to re-access this, I'll re-look it up. You know,
right?
Like,
exactly.
What's the law of thermodynamics within the?
Yes, right. And you'll just Google it and find it when you need it.
Yeah. So.
Yeah, but there were still some takeaways. Like I tried to look at it more of just what was my overall, what are my takeaways from this whole module, and I simplified it. I mean, it's so simple for a person that would be into this that they would kind of laugh at me, but at least I walked away with something. So do you have that, or is there something that you want to break down because you have more of a science background? Do you have
I mean, there were some things that were like new to me that like, I mean, there was things like I wrote down like, Einstein declares space to have ether, which is necessary for general relativity, which I was under the impression that it was the opposite. I thought that like Einstein was a big advocate of taking away the ether and having like the vacuum in space or whichever, which by the way, the vacuum in space, or space being completely void of anything and it just being like no medium at all, never made sense to me, especially when they talk about how those little trilobears, those little they're like little water bears, I think is what they're called or whatever.
Oh right, yes. Yeah. Those things are amazing.
Those things, they can live in the dead of space for 3 years and then be like unthawed and like are still alive. And I'm just kind of going like, I don't, and it's also not ever like absolute zero.
Right. Yeah, there are a lot of questions, but my understanding after this module was that I thought the same as you. Well, that Einstein was taking it away, but then later on he came back and tried to put it back in with the whole ether.
It was when he was older.
Yeah, it was like 10 years or 11 years later, but then it had already been adopted that let's look at it as a vacuum and there's no ether. They took ether out of the equation.
Right. So, I mean, like, I think like a big, which I'm sure they'll get into all this next time, but it's like, you know, there are some big holes in terms of it's like, okay, you have like Descartes talks about like there's the mind-body separation, you know, that's like the very beginning of this is what it was about. And, you know, and then they also go into the pounds per square inch of like iron and stuff and how the whole is completely unpredicted by the balancing of all the parts. And you know, and then like I know that they're going to bring that back around to, well, maybe the mind and the body aren't separate, like maybe it is all interconnected, which
Yes,
it's cool. But then, you know, and then there's they said like Newton has some more stuff to say about consciousness, like um it, they went into all of Newton's, like, you know, law of, you know, F equals ma force, and I mean they went through all of his laws of the shape of the universe being, whether it's flat, closed, open, all that stuff. And I was just kind of going like, I guess they're trying to point out how we got to where we are right now. But even within pointing that out, like I have opinions on what I think is, like, for instance, like they're saying that the universe is flat, like, and it's like a flat plane.
Yes,
and
that was one of my
and I'm kind of going like, we do a pretty good job of like making fun of the flat earthers, but we're gonna have like a flat universe. But then, like, not only that, but yeah, I just feel like, you know, that concept where it's like you can't see the entire elephant if you're too close to it, because like you're like right here on the elephant, so you can just see like his elbow or something, and you can't if you're that close to it, you can't see that it's an elephant when you step away. So like I feel like it doesn't matter if you send a couple of Sputnik probes out, or, you know, like it doesn't matter what we do, like we're in the scheme of all of this, we're so
tiny, minuscule.
Yeah, we have, or we're only from one perspective. We're on Earth. We're having this one Earth perspective.
Right.
So I don't even know why you try to figure out the shape of the universe. It's weird to me.
Right. Well, which is what I think that's module 4 and 5 are going to be about. That's going to turn away from that 2D model, because it was flat, but it was also this 2-dimensional model that all of these formulas and everything that was looked at was based on this 2D model. That was something that I also felt was an important point, that I know they're going to pivot that in modules
into, right? Yeah, I know. And I also know that it's like, I don't know how they feel about this, but, you know, they go into like Einstein's like ideas of gravity, like time dilation, like gravity lensing, gravity waves, redshift, and like black holes. Well, the thing is that, like, for me, so redshift is actually how they redshift is how they scientifically think that the universe is ever expanding, and that it's getting what do you call it, colder and colder. And so it's like, that's how they think that we came from one point of singularity. But my thing is like, okay, this was in 1920, so we have 100 years that we've been quote unquote measuring this with, like I always have to question instrumentation. Okay, so we've been measuring all this for 100 years, and you're telling me that supposedly, according to your redshift mathematics, we're 13.8 billion years old. Okay, cool. And we were all one energy point before that, and then it exploded. I don't think we have enough information for that. Like how they deduce that, I don't feel like is, if like 100 of 13.8 billion years is like not even
is nothing.
That's not even a subset that you can even
we're still doing the out breath, you know, there's still, we don't know if there's
that's true. We don't know if there's a pulsation. We don't know like to what, like, and that, like I asked, said on the elephant, like maybe it appears that what we can observe from this little angle seems to be getting cooler, but at the same time, like they even talked about
well, we'll just take down modern physics then.
We'll just take down. Well, they even talked about though how like what did he say? Protons don't actually decay in nature. And then so I'm kind of going like, so then they go into entropy, right? They talked about entropy a lot. Entropy is a measure of and entropy is a measure of missing information. But the thing is that like, for me, entropy also doesn't make sense, because we reproduce. Like even stars reproduce. There's star nurseries. There's entire star systems that are currently being born. So how are we supposed to evaporate into nothing if things are still being born 13.8 billion years later?
Well, yeah, these are all questions I think that modern physics really can't answer just yet. And will they ever really be able to answer it? Which again, which is why I think we're going to look at something different with unified physics, because it just makes sense to go in that direction.
Mm-hmm.
Yeah, like you're saying that there's not enough information for systems of measurements either. So how do we're measuring something that we've only had for a very short period of time in the scheme of things. So based
Right.
on
And
this
then
very
they
limited
do kind of talk about how there's really no such thing as a closed system. So
right,
I mean,
exactly. Yeah. So then what? So that, although that's yeah, exactly. I liked that point. Well, something just random that I had never known was this idea of white white holes. No, like the black holes everyone knows of, but then these ideas of white holes, which I didn't get like too far into. I was
yeah,
like,
what did
oh.
that one say? I must have like I have to say there was some eye glazing for me at some point because it was like reading a science
textbook. Right,
but
exactly.
I think I spent like 5 days reading this stuff, like and a lot of
Right.
hours doing this. This was like a huge physics review. But okay, so what I did right about black holes was like, okay, I summarized it for myself. I was like, so black holes are apparently when space-time gets a big enough mass to curve space-time, and it causes an event horizon, which is the radius of that edge, and a singularity occurs at the center of the object. So it's like so this suggests that infinite mass where everything accelerates at the speed of light to where it appears to be frozen in time. So it's like something that's so heavy and so mass that like there's so much light that it's just frozen. So that is the black hole. And then like the edge around it is the event horizon. So like that's like I kind of like didn't understand it to be that before this. So that was kind of interesting that's what I always just kind of thought it was sucking in energy. It was just this
like it's pulling
vacuum
you in because
portal
it's
or something.
Right.
Yeah.
And it was also such mass and had such a heavy gravitation mass. It had such heavy mass that nothing could escape its gravitational pull. Yeah.
But maybe like I guess like they are sort of, I have heard different people postulate this, that like every galaxy has one at the center of it, like, and that's what's causing the spin. Like we're all like funneling some sort of black hole. Like
was this a series also that talked about that we might be in a black hole? There are some people that think that we are in a black hole.
Oh, I haven't heard that one, but that would be interesting.
It may have been a link to video or something that I heard separately, or maybe it was
okay.
my own
Well,
thought,
there were so many other links to download and resources. Yes. Like I didn't even read any of the supplemental material really.
No, neither did I. And also, I did like the idea of these micro black holes, because that went back into the whole, as above, so below type of thing. And these black holes. The other thing that stood out for me for this was that modern physics bases the entire, is based on unknowns. So E equals MC squared is an equivalence between three unknowns.
Yeah, I wrote that too. That Nassim Haramein said that. He said like, yeah, so what is it? Like the energy, the mass, all that is
speed of light. They don't, and also the source of energy is unknown all the time. Mm-hmm. So the mathematical calculations work, but again, it's based on information that we just don't know where it comes from.
I also wrote down that like E equals MC squared wasn't actually necessary for the atomic bomb. They didn't actually have to have that equation to create the atomic bomb. And I was like, I thought, because I always was kind of thinking like, like
Einstein was the cause.
Yes, I was like he's exactly supposedly a genius and he's amazing and this and that, but at the same time, because of his science, we created the atomic bomb.
That's the way I thought.
Yeah, so I think that's what we were taught. But I guess
so.
That's not true. So that's kind of, that clears him. I like him even more now.
Exactly. I was thinking the same thing. I was like, because he was also a peace activist, as far as I understood. Right. It was like at least pacific in nature.
But I mean, like just time being relative to the observer, or, or even being relative to your space and where you are. Like, so like somebody on the moon is going to have a different experience of time than someone on the earth, because it's like your rotation to your center sun or whatever. It's like where you are physically. And like that was a concept that didn't even exist before he thought that. And that's amazing. Like,
Yeah,
it really is.
it's pretty cool, right? And the whole, if a train is passing by and somebody's on the train, they bounce a ball versus somebody that's watching the ball bounce on the platform and the train going by, how it moves differently, because the person who bounced the ball on the train would just see it go up and down, where the person watching it go by would see it go up and down, but actually having moved.
Right. So it's relativity. It's all about
relativity.
Yeah, which is an amazing, that is genius, really, to come up with that on your own.
Yeah, and both are correct. I love it.
Mm-hmm.
Yeah, that was a good reminder, because I had heard that before. My dad and brother used to like to talk to me about physics, and I like this stuff. That's how I do, but it's very marginal. So I would hear this and be like, "Oh wow, that's really cool," But yeah, that's true. That concept at least wasn't written down if it had been thought of before Einstein.
Well, and then one other thing that Nassim says about the black holes is like, and I guess we'll probably get into this in number 4, but he was saying that like Nassim thinks that black holes were there or present prior to the galactic formation, so during the early universal evolution, and thinks that collapsing into singularity to produce a supernova explode. Thus black holes are, I can't read my own handwriting, something force it, are black holes are the driving force, not the result. So that was it. So he's thinking that like black holes may,
be the creator,
cause singularities, cause explosions, cause these things, versus be the result of because like right now I think we sort of have, for a long time they thought they were
everything
is
going to it.
Yeah, and like that they were also they were like dead stars that collapsed in on themselves and turned it. I mean, like he's thinking, no, these predated everything else. Or
yes, well that does seem to make sense, or at least both are correct, because it's like the constant circle of life that would go on at this galactic level. Like something ends and everything goes into it, and then there's a singularity and it's born again out. Something else is born out of it.
Mm-hmm. Yeah. I also found that this is the other interesting things, like when they started getting into more like quantum mechanics, they got a lot into like Max Planck and Niels Bohr, and then like Schrödinger.
Yeah, that was tough.
That stuff got real dense for me. But like like the double slit experiment is like where light can be observed as a particle and a wave, and then Schrödinger's cat is basically
dead and alive.
Like the dead cat taking poison. It's like it's such a dumb experiment. Could you not do something else besides that cat? But it's supposed to be like observation of.
That's right.
It's about it's about like something is
what you perception
is reality. Yeah, like observation is a causality of reality or something, whatever. But what I thought was interesting is that like they were saying that quarks have actually never been observed in nature. You can actually only observe, because quarks are even smaller than they're inside the protons, and when you collide the particles in the CERN thing, or whatever,
that cool thing that spins.
So they were saying like they're acting like they're a fundamental part of nature, but yet we've only ever observed them when we're colliding particles at like as close as we can get to light speed. So maybe they're not as fundamental or formational as we think, since that's the only time we've actually observed them. And so that's kind of interesting. This whole thing does make you kind of go like, we still have a lot of holes. And why I think we have a lot of holes too is because of how dense this shit is. And like you end up like studying it going like, oh my God, it's almost presented in a way that they don't want a lot of people to dig into it. I feel like, not them, but I'm saying society.
That was part of the summary of the of this unit, that if you were a physicist or somebody that has been studying something so into it, and you were very into the mathematical equations of it and going over it and over it, and spent your life doing that, because this is such complex information, that at some point if you stood back and said, well, actually, this very well could be incorrect, and we have to throw all of it out, or at least most of it out, then, or look at a completely new model, then your entire life's work would be not down the drain, but at least be, completely different than you had expected or thought it was going to be. So what kind of establishment is going to want to actually say that? And if each person, if there are people who are really into string theory, for example, or just focusing on just that aspect, these physicists are so into whatever it is that they're focused on, that it's hard to then to go into other areas, because their time is just consumed by doing this very one important but very
well
specific thing.
The thing is like, but yet we do actually have real practical things that have been built with current modern day physics. Like we understand like the engineering of like how much pressure like and forces like a bridge can hold, or a skyscraper can, or like or like the ways in which like the airplanes, or all the things that we have in our life are what we have figured out with all this stuff too. But my thing is just that it's not done.
Well, that's also a different type of physics, and we're also the laws are different.
This is more theoretical stuff too.
Yes, that's true. And it's also cosmic, where we're looking at practical everyday physics that work under the laws of physics that we know on planet Earth. So they're really good at that, because we're in that dimension.
We're here. Yeah. Who knows what it's going to be once we get to Mars.
Right. So I don't think, when I was thinking of modern physics, I wasn't thinking of more like, what is the name of that physics? What is that type of physics when it's like everyday physics? No. It's everyday physics, like just like what you're talking about. We know how much weight we need to put on a bridge, how a bridge should be built, so it doesn't get like, it's practical, it's everyday use. But that physics seems to be very well established, and thank goodness, because that's how we build our infrastructure. But outside of that, the laws of physics change, which is what Einstein was really, looking at, I think, and all the big like theoretical, like you said, theoretical thinkers.
Yeah, I also thought it's interesting that
applied physics.
Applied physics. Okay, yeah, exactly. Applied versus theoretical physics, right? I guess theoretical physics is all the fun stuff, but applied is just which yeah, you're right. Applied physics, theoretical physics. Okay, and I guess we really are kind of more looking at theoretical physics in all of this. But yeah, like even just things like I don't know. We've never like our Higgs boson. Like the Higgs boson is it's a meditating particle. It's a hypothesized field that all particles interact with and thus acquire mass. But it's not actually really like observable.
Yeah, that's crazy. It kind of reminded me of when you're looking at a star, and when you look at it, you can't really see it, but when you gaze at it, or
right, it like bleeds when you actually look directly at it.
Yeah, it doesn't. Yeah, but if you look right next to it, you can see the star, but from your peripheral somewhat, or just like right out of focus. That's kind of what that reminded me of, but I think that's overly simplified.
No, maybe not. I like that. I like that analogy or hypothesis.
Well, it's also like, the experiment with the observer and everything with the closed system. You just can't, if you're going to observe this, well, maybe that's not with the closed system. Maybe I was completely misunderstanding that. But like if you watch some kind of experiment, of course it's going to you can never not observe it. There's always an observer in the experiment, so that's going to somehow affect the experiment. Is that's also what that reminded me of. But again, by that point, it was like really late into the unit, and I was like, oh my gosh.
No, yeah, like so long. I was like, oh.
It's tough. I did like I listened to most of their conversation about that they had their Zoom chat about this unit. It wasn't really about the unit, because they don't get into the details of it, but they talk more about it in general, and that was helpful. I thought that listening to it was like, okay, yeah, good. Because they did say that this was really heavy. They're like, most people stop here.
Right. But they also said, like, you don't have to memorize all this. You don't have to know it heart by heart. It's just like a refresher and take away what you want or whatever. But,
Yeah, it was like, what refresher? This is completely, most of it's new. I just had heard of it basically in the past.
So. There is this YouTube channel that I love called Kathy Loves Physics and History. And I've been watching it recently anyway, because like it's kind of like helping me with some of my magnet ideas and stuff. Like she has like a whole, like she goes through and explains how electricity works, like from the beginning to the end, like, and she'll do 40 short videos, and like every new video will be about like, this is,
oh, cool,
about Einstein, this is Planck, this is like whatever. And then she's so good. You have to watch her stuff. I'll send you some links. In fact, I'll like copy her link for everybody, because I actually feel like hers is more
better broken down,
bite-sized. Yeah, like more bite-sized video clip. That's the other thing. I'm so ADD that anymore, like technology has ruined me, that I cannot read this much anymore. I am like, I did it, but it was like I literally felt like I was in, like, had to study for a test. I was like if we weren't doing this together and I wasn't held accountable at all with you, I would be like, if this was just to my own vices, I would have been like, I'm gonna watch YouTube.
That's the same thing here, because at the beginning there were videos, but then they stopped, and then now there's just every now and then maybe a short video,
and it'll be like a 2-minute video with 8 pages to read. You're like,
right, exactly. But somebody I was going through the forum, and somebody commented that it would be nice to have at the end of each unit Nassim summarize, or one of
somebody summarize each thing,
summarize it, or just or give their perspective on it, or something that's more palatable. That's maybe a critique of the course itself, but that would be helpful. So
because as it stands, it's a little bit too maybe formal academic way of a class being conducted or being taught,
Right. And they probably have that for a reason, especially when they're getting into unified physics, and they want you to have this understanding of physics that it should not be watered down, that they're getting their point, that they are award-winning physicists that are allowed to have that they have the credential to have this type of theory that may be the new shift. So they need to have that there, and I get that. But for like the lay person, summary would be nice. Or just
it's like, like I'm 37 years old. I don't think I'm gonna, become.
I'm not changing my career.
Yeah, exactly. Here, I don't know what I'm gonna do in life, but like right now, I mean, maybe I'll go grow a vegetable garden or something. But I don't think I'm gonna exactly become a rocket scientist. Maybe.
Yeah, you never know.
You never know.
Well, you might be doing something with magnets, so who knows?
There's that. Yeah. Okay, so wait, is there anything else that really stuck out for you?
No, I think that was it. Basically, I think we touched upon everything. And so I don't know if that was too watered down. Oh, at the end, they did kind of summarize. I did like the summary that they said. Our fundamental understanding of each term is incomplete. What is mass? What is energy? What is the speed of light? And why is it constant? So there were a bunch of questions that were still unanswered, which obviously are important. We have to look at it, which is going to hopefully open the door to Unit 4.
Yeah, and I also kind of thought about that too, with when they were talking about the speed of light, and they didn't actually mention this, but like my brain sort of went to this, like, because the speed of light is constant. That's a constant. Like, that's just a thing. That's a thing. But then part of me kind of goes like, well, what if that's relative too? What if that's based on its speed of light is all constant within our solar system, maybe even our galaxy, but maybe it's not everywhere. Maybe
exactly
like, these light I mean, I don't know, like, maybe, I mean, especially when like, I don't know if you watched that one little video when they were doing the double slit experiment at MIT, but they were
Yes.
talking about how like not all light works equally within the double slit experiment. Like, for
Right.
instance, like
Like
they were
laser.
using laser light, which like worked really perfectly, but then when they put like a flashlight in, it doesn't do the same exact thing, and then you're kind of going like, well, and they were talking about like how it has, like, the light has to be filtered a certain way or this or that, and I'm like, so even not all light like works the same in all experiments. So I don't know, I'm just kind of thinking, yeah, lights, sure, I'll tell you, I'll obviously, as a person who's a big UFO experiencer and seer and lover and all that stuff, like, somebody's got something else figured out that we don't got figured out, all right? And I'm saying,
Right.
like, there's some speed of light stuff that's been manipulated somewhere along the line. And like, people are saying, well, no, it's not been manipulated, it's just they've figured out how to bend space-time. And I'm like, that's manipulated. But
Right. Yeah, well, maybe it's their understanding of manipulated. But anyway,
right,
yes,
right.
I see what you're saying, manipulated. Yeah. Like they're able to, yeah,
I
that's
mean,
another word, manipulate.
you could go
Negative
with the
content.
whole like, no, it's not true.
Right.
UFOs don't exist. None of that's ever happened, and blah blah blah. And I'm just crazy, and lots of other people, and that's fine. You can go with that if you want to. That's cool. But like, I don't know. I'm just thinking maybe
Yeah.
not.
Well, yeah, I think that your point is good because it goes back for me. We had this conversation last time, like at the end, we were kind of mentioning. So if we're in this fractal holographic universe, and
Mhm.
that's what we're in, and does that, are there other universes that aren't part of this universe in that, or are they separate fractals that aren't at all like ours? And then in that case the speed of light would work differently, or that maybe there wouldn't even be light, maybe we can't even understand what there would be.
Yeah, that's true. Like, there could be a whole other set of things that our senses don't perceive.
Yes. Yeah, I know this is not related to this chapter, but something that I was thinking of is like, if we're in, if supposedly, if we get into the whole esoteric part of it, it's like, oh, we're based on love, and ether is this whole like love, I don't know, let's say if everything is love, this doesn't
Okay.
again have to do with physics, then, and that's what this universe is based on, or like that's what it is. I'm like, is there another universe that's not like, is it like anti-love, is there like
Or hate,
everything
or
is,
yeah, who knows.
yeah, totally. I was like,
See,
oh,
but
I don't.
then that's why that's when I sometimes think of like, well, maybe, and I don't think this universe is completely based on love, because we still have war and stuff like that. So I think it's probably more, I feel like we definitely live in a duality, but there
Mhm.
might be both. Like, I
Right.
guess that would be the concept of heaven or hell, right?
That's true. We do live in a duality. So that's, yeah, at least in this dimension. But I think overall, if we were looking at many dimensions in the whole universe thing, then I would think that it would be love. But in this third dimension, it's duality. And you can see that both sides.
It's
Anyway, who
interesting.
knows?
Like, I really do think a lot about um the holographic principle of, like the one part contains all the information for the whole, and it's even like down into our all of our DNA has like 3 billion or 3 trillion like segments or something. And I thought, I was asking somebody about this, like one of my doctor friends or something, about how, like, okay, so like you're saying that like a drop of blood, or like a piece of DNA that comes from my finger, um, and one that comes from like my liver, have all the same information. And it's like, well, then how does every cell, if I start out as one cell and I divide it, and then I whatever, like, how does every cell know like what to become a fingernail
It's
cell
going to
versus like
become.
a liver cell or whatever? And there's a word for that. I can't remember what that is, but it still means that every cell has all the information of your entire body in it. It's just like
Mhm.
it is acting upon as this one that it is, which that's really crazy and fascinating. And like,
Yeah.
what
Because that
are
brings in the
we?
whole question of consciousness and their communication with each other.
Yeah, and the
Yeah.
interaction of, yeah, and being, and yet I am one fluid being here, but made up of trillions of
Right.
cells, particles, atoms, like whatever you want to call it. And then and I'm one of billions on the planet.
Right. Exactly. And if we're all fractals of the same,
Yeah.
we can access all that information at some level. Yeah, that's the stuff that I like, but I don't know. I'm excited to see if unified physics can actually
Start
prove
putting
this,
some stuff, or
or at least go in that direction.
Or if they're even thinking about this kind of stuff. We don't even know.
That's true. We don't know. Although I have a feeling it is.
Yeah, I would hope.
Yeah, I mean, and the word itself is unified. I don't know. We'll see what that means. Cool.
True.
I have nothing else to say about that unit. I'm glad it's done.
Goodbye, modern physics unit. It was real fun. Thanks.
Yeah.